Alright, what's up guys? Today we're going into our first lesson that kind of scratches the surface of calculus. Maybe a little bit, maybe not. Depends on how you interpret it, but today we're going to be looking at rate of change, but specifically we're going to be looking at the average rate of change. So I'm sure everybody's quite familiar with the average rate of change. We got pretty used to it. So what are some so we're going to be looking at an example. So this example right here, the goal is to calculate and interpret the average rate of change on an interval of an independent variable. And we're talking about bacteria population, which is pretty classic. Everybody loves bacteria. Okay, not really. But yeah, it's very classic. It's definitely a classic example that you come over, whether in biology or in any other classes. It's definitely a popular example. And then they gave us some time periods. So 2 hours, every 2 hours, they measured the number of bacteria within these population, with this population, I guess. And they gave us an updated number. So first, we're going to be reasoning about the rate of change. So we're going to be using the data in the table of values to determine the 2 hour interval in which the population grew fastest. So we're going to see which of these did the number of bacteria, like just double or triple or quadruple, which were the fastest. Okay, so how do we find the average rate of change? Now you might be questioning, how do we do that? Well, we have a little formula here that I'm going to just copy and paste right here. So, okay, not really. I'll be introducing. We're not going to really derive it, but we're gonna be understanding a little bit more. Hopefully, you got an understanding of this in other classes, specifically physics. You should be really good at this if you took physics. Okay, so we have our table here, and how do we find the average rate of change? Well, let's name the average rate of change. What should we name it? Let's name our average rate of change delta x. So delta x. Delta x. This is our average rate of change. Okay, sounds good, right? Sounds good, guys. Delta x is equal to, what is x? What is it equal to? Well, we want to delta x is equal to, right? It's talked about the independent and dependent variable. It should be equal to the change in y over the change in x, right? You might be familiar with this. Like, oh wait, hold on a minute. I heard this before. The change in y over the change in x. What is this? This is a slope. Exactly. Otherwise known as the slope. So when we have a slope, this should be so much easier. So if you want a formal formula, it will be f of x minus, f of x initial. So f of x final minus f of x initial over x final minus x initial. Right? This is how you should do it. This is how it's reasoned. Right? And now let's go ahead and use our little table value here. So let's use this formula on our table. So let's see. For the first hour, 1122 minus 850 over 2. And this roughly gives us what? 136. 272 divided by 2, so 136. And then for our second hour, we'll have 1481 minus 1122. What will that give us? That'll give us 179.2. 179.5. And then keep in mind there's a bracket here, right? So we're not too confused about that one. There's a bracket here, so everything over 2. Okay, this is how it is. And this is approximately it's not approximately, it's exactly 179.5. So right away we can see the rate of growth in the second hour is already higher than the first hour. Now let's see our third second hour. So our third interval. So 1954 minus 1481 over 2. Right? Because it's 6 minus 4. So let's see, over 2, that will give us 236.5. And then we'll have 2577 minus 1954 over 2. Wow, that's a lot. That's a lot. So 311.5. And then 3,400 minus 2,577. That's even more. So that's 411.5. So we're like, wow, this is doubling, tripling. This is growing really, really fast. And using this data, we could find out that the greatest change in bacteria population occurred on the very last interval from hour 8 to hour 10. With an average increase, now we round up, with an average increase of 412 bacteria per 2 hour. Per hour. My bad. Per hour. Right. And now we're done example 1. Let's go ahead and look at number 2. So number 2 is completely different. It's another different question. It's a different question. It's not the same example anymore. So let's go ahead and move on to our example number 2. So reasoning about the average rate of change in linear relationships. So we're looking at Sarah. She rents a car from a rental company. She charged $35 a day and a fee of 15 cents per kilometer for the distance she drives each day. The equation C of D is equal to 0.15D plus 35 can be used to calculate her daily cost to rent the car, where C of D is her daily cost in dollars and D is the daily distance she drives. Discuss the average rate of changes in her daily cost in relation to the distance she drives. Okay, so we have this function. And sometimes when we don't know where to start, it's a good thing to graph this function. So let me go ahead and graph it for you. You should do this on your own, by the way. So I have this graph. This interesting linear graph. Obviously, it's quite linear. It's quite straight. Obviously, it's a clear linear situation. Let's see if it matches. So we have a y-intercept of 35, which is present on the graph. We have a slope of 0.15, which is also quite present on the graph. So sure, this graph is the correct graph. Let's interpret this graph. So to interpret this graph, let's see. The relationship is clearly linear, so the rate of change of daily cost is constant, right? The daily cost doesn't really the rate of change of the daily cost is constant. It doesn't change. Not just because I drive an extra kilometer doesn't mean they will charge me more for the next kilometer. The first kilometer that I drive is equal to the amount they charge me for the last kilometer I drive. It's the same price every kilometer. So this means that no matter between any 2 points, they will have the same slope as any other 2 points. So let's just go ahead and pick some, 2 random distance interval to prove that we are right. So let's pick the interval from 0 to 100. So picking the interval of average cost from 0 kilometer driven to 100 kilometer driven. And we will also have, let's do, 100 to 250. Sure. So picking the interval of average cost from 0 kilometer driven to 100 kilometer driven, from 100 kilometer driven to 250 km driven. All right, so let's look at this. So let's look at 100 first, obviously 0 to 100, because that's what's ahead. So let's use our formula that we just derived a few minutes ago, the average rate of change formula. So we'll have C of 100 minus C of 0, and everything over 100 minus 0. Let's go ahead and write that down. Over 100 minus 0. Perfect. So let's go ahead and plug C of 100 in. So C of 100 is just 100 times 0.15, which is 15 plus 35. And what does that get us? 15 plus 35. So hard. So 50 minus 35 over 100 minus 0 being 100. Now 50 minus 35 is 0.15, and 0.15 divided by 100, it's 15. Then 15 divided by 100 is just 0.15 dollars per kilometer. Never forget your units, guys. So the average rate of change of cost between 0 kilometer driven to 100 kilometer driven is 0.15, 15 cents per kilometer. All right. Let's go ahead and move on to our second interval. So pick an interval of average cost from 100 to 250 kilometer driven. So C of 250 minus C of 100 over 250 minus 100. That's going to give C of 250. Let's plug that in. So what's 250 times 0.15? So that's 37.5 plus 50 plus 35. So 72.5. 72.5. Okay, I'll just write the entire thing out. 72.50 minus 50. Because C of 100 is 50, right? Plus 50. And then, minus 50. And then this is O divided by 250 minus 100. So 150. And what does that get us? Well, we have 22.5 over 150. That's still 0.15, right? $0.15 pretty simple. And look at these. What do we see? We noticed that the average rate of change of cost is the same. This is because we have a linear relationship and the slope doesn't change. Perfect. We just discovered that in a linear relationship, for every extra kilometer she drives, her daily cost increases by 0.15 cent, and it doesn't multiply by higher. Let's go ahead and move on to example number 3. So let's have it here. So example number 3 is a pretty big question. Should be pretty interesting as well. So we have a question using a graph to determine the average rate of change, which is kind of hard because we never do it. We never did it. For this question, we used our graph, we analyzed it, but we technically still used the algebraic solution. So Andrew drains water from a hot tub because he thinks, it's too hot. The tub holds 1,600 liters of water. It takes 2 hours for the water to drain completely, and the volume in liters of water remaining in the tub in various time t in minutes is shown on the table and graph. So we graphed this, they graphed it for us. Okay, so it looks like. As time goes on, less and less water gets drained. Does it make sense? Doesn't matter. So let's calculate the average rate of change. So as we know, we're going to be using the same formula because we can't really get creative within the same lesson. So A, and this is question number 1. C of 90 minus C of 30 over 90 minus 30. Because we have time in minutes right here, we don't have to do any fancy stuff in the denominator. If we did have something else, we might have to do a little bit of fancy stuff. But either way, we don't have to do much fancy stuff here. So let's go ahead and do that. So obviously you can draw secant lines. So you could draw a line from 30 right here to 90, which is over here. But you could also do it algebraically. So if you use a secant line, you're going to get 100 minus 900. So it goes 100 minus 900. And this is over 60. Which is going to give you negative 13.3. So I hope you guys can do the both methods. Try out both methods for both rest of these. And let's talk about B. So why is the rate of change in volume negative during each of these time intervals? Right? So why are they? So the volume decreases, right? The volume decreases. The rate of change in volume is negative because as time increases, the volume decreases. The volume decreases. So the numerator in each interval calculations is negative, while the denominator is positive. And because of this, this makes the rational number that represents the rate of change to be negative. Okay, makes sense. Let's also talk about, why this intuitively makes sense. The water is flowing out of the tub, so the volume that remains will always decrease. Okay, that makes sense. Let's talk about C. Does the hot pot drain at a constant rate? Well, there's 2 ways to look at this. One is that you should have calculated all of these intervals, and you should be like, oh, it is not, because sometimes it decreases faster than the other. But just by looking at this graph, we can tell it's an exponential decrease. So as time goes on, we're draining less and less and less and less and less water at the same time. So this is an exponential decrease. So C, no. The water is not draining at a constant rate. And you have to give your rate reasons. So this can be seen from the graph. This can be seen from the graph as it is clearly not a linear relationship, right? And you guys could give other explanations. You could talk about, looking at the slope calculations. Some of the lines have greater slope than other, blah blah blah. You guys can name your own reasons. Now let's talk about our final example. So we're gonna be using some examples to determine the rate. We're gonna be using equations to determine the average rate of change. And now we're going to be working with purely just, functions, right? This is where we get back to our main thing. We're still function workers. So rock is tossed upward from a cliff that is 120 meters above the water. The height of the rock above the water is modeled by this function h of t is equal to negative 5t squared plus 10t plus 120, where h of t is the height in meters and t is time in seconds. Okay, that sounds interesting. So let's see what we can do here. Let's calculate the average rate of change in height during each of these following intervals. So this time, we'll actually be using just purely functions. Wow, we haven't done that before. We haven't done that with any of these. Some of these we could just see with graph. Others we could just plug it in. But this is the first one. We'll actually be using functions. So let's talk about this. So I'll only be doing one of them because you should be able to do the rest. So I'll do, I'll do 3. How does that sound? So h of 3, so the top should be h of 3 minus h of 2 over 3 minus 2. So let me make this a little wider. Okay, so we have this. So go ahead and calculate. So h of 3, that's going to be equal to, what is going to be equal to? H of 3 is going to be equal to, hold on. H of 3, so negative 45 plus 30 plus 120. So that's going to give us 105 minus h of 2, so minus 120. And that's going to be O over 1, which is going to equal to negative 15 meters per second. Let's think about this. So at time 2 or 2 or 3, the rate of change is negative, meaning that the rock is falling down. Does that make sense? That surely does make sense, right? It's falling down. Okay, and as time increases, what do you know about the average rate of change in height during each 1 second interval? So you should have been done 1, 2, 4, and then you should have noticed something. But obviously, we should notice something too because we study physics. Hopefully, you study physics a little bit. Hopefully, so the average rate of change are positive and then negative because the height of the rock increases, right? So the average rate of change of the rock is first positive, and then negative because we threw the rock up, and due to gravity, the rock falls down again, right? And and after 1 second, as time increases, the rate of change of the rock also increases. Why? Because the magnitude of the average rate of change is increasing because the rock is not falling at a constant rate. It is accelerating due to gravity. Finally, let's answer question C. Describe what the average rate of change means in this situation. So, since the rate of change compares the distance traveled over an interval of time, the rate of change here represents simply the speed of the rock during a given interval. And with that said, we are done all of our examples. There are some points that I didn't do. These plugging in simple math, you should be able to do these yourself on your own. And finally, we will have our some summary and a little bit of our conclusion, which is on our right. Let's go ahead and see that. So where is it? It should be here. Okay, let me play it steady. Okay, here. So, what is our key ideas? The average rate of change is the change in the quantity represented by the dependent variable, which is y, divided by the corresponding change in the quantity represented in the independent variable, which is also our x, over a certain interval. So algebraically, the average rate of change for any function is y equal to f of x over the interval x initial less than x final, which can be determined by this little formula here. The average rate of change is change of y over change of x, so dy over dx, which is how you say it in derivatives. But you've seen this before. Definitely seen this before. So this is our formula, and graphically, the average rate of change of any function y equals to f of x over the interval over here is equivalent to the slope of the secant line passing through 2 points. So if I want to find the average rate of change here, I would just have to take this take this point and take this point, draw a line across it, find the slope of this secant line. So average rate of change is equal to the slope of the secant line, which is still increased the same everything here. So change of y over change of x, and y2 minus y1 over x2 minus x1. So basically your slope formula that you learned in grade 10. Anyways, what do we need to know? The average rate of change is expressed using units of two quantities that are related to each other. A positive average rate of change indicates that the quantity represented by the dependent variable is increasing on a specific variable, compared to the quantity represented by the independent variable. Graphically, this is indicated by a secant line that has a positive slope, which is what we have right here. Although linear relationships have constant rate of change, as we have saw in example 2, average rate of change calculations over different intervals will have the same result. And nonlinear relationships do not have constant rate of change, and average rate of change calculations over different intervals of the dependent variable will give different results. With that said, we are done our first lessons of rate of change into Unit 2. I hope you're doing your homework, which is on page 76, 77, and 78. There are 15 questions, and you can just skip on all the even numbers and do only the odd numbers. Anyways, guys, have a great day.